Course 1 in Lesson 96, we're being introduced to a topic that many times gets left for pre and regular algebra, but we're going to attempt it today. We'll go slow and make sure you're feeling comfortable. It's called functions, and then we're going to see about graphing them. We've talked about formulas. They're kind of similar to functions. A formula could be area is length times width. And to solve for the area, we need to know the value of L. We need to know the value of W. We put in these amounts to get this amount. It goes out. Put this in, get this out. They have an even better example for you in a moment. One more review though. If I told you this and x is worth 2, can you solve that? X is 2, so this is worth 2, okay? 3x means 3 times 2. Just to make it neater. 3 times 2 plus 1. 6 plus 1, 7 is the answer to 3x plus 1 when x is 2. Okay. Surface area of a rectangular prism is probably a better example than what I used because it's only got one letter on each side of the equal sign. We know a cube is a special kind of rectangular prism with 6 square faces. And we know with the area of one square is just side squared because both sides are the same. That's one face. Well, there's 6 faces. So we can find the surface area of the square by saying side squared times 6, I guess. Now, this left side is not a side of a cube, it's the side of a square, it's the area of a side. So if we're going to let S mean area, I don't know, I'll just say, let's just stick with A. Area of a side. Maybe I'll do a little S. Area of a side. If 4 is the area of one side, and we've said that just 6 faces would be the total surface area, then 24 is the surface area. If 9 is the area of one side of a cube, then 54 is going to be the area of the whole cube. What's the rule that's being followed? A pattern, kind of, between this number and this number over here. The input number gets multiplied by 6 to get the output number. In, out. And what is happening in between, we don't have to show. It's really 6 times the area of a side. It's a formula. But you can think of it as like a machine that's happening right here. And I stick this ingredient inside, and it shoots out this answer on the other side, if that makes any sense. Using this table, we can see how this is happening quite easily. And we're going to make and interpret more tables. These tables illustrate a function. In example 1 here, find the rule for the function. We don't know what L or M stand for, but we can still determine what's going on between them to take the input and get the output. The same rule is happening for all 4 rows. Can you determine what the function rule is in all of these? Well, you can try different things. Guess and check. 5 times 4, is it that we always multiply by 4? don't know this one yet. How about this one? 4 times 10 would not be 25. If I look at 15 times 30, it almost looks like is it times 2? Well, that didn't work because of this one. It can't be a subtraction or division because the numbers are getting bigger. How about addition? What do I add in, let's say, this one? 15. How does that work for the rest? Oh, okay. We add 15 every time. It's the rule for all of them. So, the rule for the function is that L has 15 added to it to get to M. So you could even create a new table where we've got L on one side and L plus 15 on the right side. Input L, output L plus 15. And then we fill in 7 plus 15. 22 goes here. Okay? Couple more pages here. Here's one of these algebraic expressions I wanted to make sure you felt good about in today's review. This is a horizontal table, but it works the same way. Think of it as, being organized this way, but it's just flipped on its side now. And we've got this part here. Start with the top. When x is 2, what's the output? 4. And for this one, they put the rule in there right here for us. The rule is 3x, minus 2. When I know x is, let's say, 3, then 9 minus the 2 is 7, right? So what would this 4 become? If 4 is x, the rule will make it what after it's gone through the function machine? So we can just quick do some algebra. 3, put a parentheses where x belongs, minus 2. 3 times x was 4 minus 2, which is 12 minus 2, which is 10. Answer 10. You can also graph these with a t-chart. S is 1, P is 4. This is showing perimeter of a square's relation to each side length. So you graph according to the labels. Looks like horizontally, x-axis, we're following length of the side. So length, the first length was 1. You go 1 over, and then to decide how far up, you look at P. P is 4. So you go up 1, over 1, up 4, and I stop there because notice the count here is not by 1s, it's by 4s. So this is my first dot. Then 2 was 8, up 8, and so on. You have to be very careful that you're looking at the labels of both sides and the increments they're using for each side, that you label everything properly and you graph this properly. We've used different scales on the two axes so that the graph is not too steep. It'd be harder to read if they used 1s all the way up vertically. The graphed points show the side length and perimeter of 4 squares with side lengths of 1, 2, 3, and 4. Notice that the graphed points are aligned. Of course, we could graph more and represent squares with side lengths as high as 100 if we wanted. We could also graph points for squares with side lengths of less than 100th. In fact, we can graph points for any side length whatsoever, and they would fall on the line. It's following a function rule, and that's what's going to happen. That's why we can put an arrow here showing that all of these will follow the same rule. Now in example 3, the perimeter of an equilateral triangle is a function of the length of its sides. Make a table using side lengths. Let's just pick 1, 2, 3, and 4 units. Graph the ordered pair on a coordinate plane. So we create a table. Maybe it looks like this. You could just write a basic T if you want, and label S and P. The perimeter of an equilateral triangle. What do we know about equilateral triangles? Sides are all the same. And what do we know about triangles? There's only 3 of them. So they didn't tell us the function rule per se, but we already know these things. So if side length is 1, they said use 1, 2, 3, and 4. Then perimeter would be 3. Perimeter would be 6. Perimeter would be 9 and 12. The function rule is multiply S times 3 gives me P. And then you can graph over 1, up 3. Looks like they have increments of 3. Over 2, up 6. 1, 2, 3, 4, 5, 6. Okay? And so on. And you graph all 4, showing the dots for each, and then putting an arrow at the top. Every point along the ray represents the side length and perimeter of an equilateral triangle. They all follow the same rule. So we went pretty slow. You can always pause, rewind, look back, play it at a faster pace. Let this video be a resource to you. I hope it's helpful. Let these example problems in the book be helpful to you as you get acquainted with the concept of what a function rule is and how to make tables and graphs that correspond. I'd like you to pick either A or B, and either C or D. And let's try E, maybe find a partner for that word problem pertaining to functions. So 3 total today.